and thank you for the invitation. It's been a great 2 days visiting Stanford and speaking to a bunch of people. Oh, scary. Okay, but first and foremost, I'm not a roboticist by any stretch of imagination. I study solid mechanics and design and computation, but I don't study robotics. In the past, I have done some robotics-like adjacent projects, and I'll talk a little bit about that, and a little bit about how do we control the shapes of, typically speaking, soft robots. So that's what we're going to focus on. So I took from Wikipedia the definition of soft robots. The goal of soft robotics is the design and construction of robots with physically flexible bodies and electronics. So I was familiar with all the parts except to the point of electronics, which is quite interesting because we also want flexible electronics to go alongside with the flexible body of the robotics. And in terms of mechanics, it's quite interesting. Okay, before this, in terms of mechanics, it's quite interesting because I was thinking about how do you define softness. So with traditional robots, I was thinking you have bodies whose stiffness is much higher than the stuff you're trying to manipulate. So you don't need to consider the elasticity or the mechanics of the robot itself, which to me makes sense, right? And then the second thing is hard robots, rigid robots, typically have a fixed number of degrees of freedom, which you can control explicitly using very sophisticated control algorithms, and these are finite. When we go to soft robotics, then the problem becomes a continuum problem where every bit of the material can deform alongside with the stuff we're trying to manipulate. So here are two homegrown examples from Stanford. One is from my host, Allison, with a vine robot with inflation-based extension mechanisms. And the second is from Renee Zhao, where she is using a combination of crystalline patterns and magnetic discs, which you can see in the black. I don't know if you can see it. These little black discs with programmable magnetic domains, which interacts with the external magnetic field to exhibit different controlled locomotion. So in all of these examples, it's very hard to kind of define how many degrees of freedom we have, because every bit of the material can deform, and each material point has at least 3 translational degree of freedom and 3 rotational degree of freedom. So it's kind of hard to kind of define how do we control such a thing. But there we go, right? This is the paradigm of soft robotic, or approaching the notion of soft robotics. And I kind of want to simplify this a little bit because it's too difficult to control a continuously deforming elastic body. We want to go back a little bit and look at some mechanics which, through nonlinearity, actually simplifies the behavior. So this is one mechanical system. It's a light switch. And as you all know, when you flick the light switch, you need to apply a little bit of force, and you can feel at first it's hard to push, and then once you snap through the halfway point, it just snaps to the other side. And you can let go of the switch at that point and it will stay on. And if you want to turn it off, you would do the opposing motion and you push the other way and it'll go back. It's very common. I mean, I'm explaining light switches to you. But the point is, mechanical systems, material systems, sometimes exhibit this type of very nonlinear behavior, which is something you don't conventionally think about. If you take a piece of steel, you can model a piece of steel like a spring, which means you push by 1 Newton force, it will displace by an X amount. You push 2 Newtons, it will displace by 2X amount in a thing we call linear elasticity. But this doesn't do this, right? This is something that's decidedly not linear. So that's one. The second is something you, again, have experienced many times over without knowing it. If you ever played with steady putty, so the stuff you can mold very easily if you press onto it very slowly, but if you try to hit it with a hammer, it will shatter. So that kind of materials depend on the rate at which you apply the force. The faster you apply the force, the stiffer and more brittle the material will be, and vice versa. So we can take advantage of such viscothermoelasticity to pretend it's a power source instead of the use of external batteries and such. So these are the 2 ingredients, and we're going to show that these ingredients, if we kind of smartly apply these to engineering systems, we can do many interesting things. So the first is, this is very old, it's from my PhD, so if you excuse me, this is an autonomously deploying solar panel-like array. And this is entirely 3D printed, and the contribution here is the source of power, the actuation mechanism, is distributed everywhere on the system. So there's not a distinct location where, that's the actuation mechanism. Everywhere, 100% of the material is deploying itself. So that's one. Number two, shape morphing. So we want to see if it's possible to not only achieve morphing of shape, but to achieve targeted morphing of shape. The notion is, if we, as soft robotics, you need to have precisely controlled shape, right? Shape control is quite important, and we want to see if it's possible for the user to specify exactly what shape A is and what shape B is, and how to go from shape A to B. And the second question in this project is, once it reaches from A to B, is it possible to make it stay in B indefinitely? And it will never go back to A ever again. So we don't need to keep like the light switch, we do not need to keep the force there to keep it on. And the last one kind of combines the shape memory polymer effect and the mechanical biostability to achieve a material-based locomotion. So this is very primitive compared to actual robots, but it demonstrates the notion of how do you locomote without any electronics. So these are the three projects, and I'll talk about them in turn. The first one, this is the result. This is the result. It's entirely 3D printed, and you can see the middle and to the right are both 1-to-1 scale. So this is the amount of expansion we get. We were targeting exactly a 10-fold areal expansion, and that's what we got. And the notion is we can go from the center to the right without any human interaction. It would just autonomously expand. And we achieved this through the 3D printing of shape memory polymers. So shape memory polymers is a fancy word for many, many thermoset resins, which all exhibit this phenomenon at different temperatures. The idea is we're going to 3D print something like this. This is just an idealized version of polymer chain in a room temperature. And we first heat it to above its glass transition temperature, in which phase transforms from the glassy phase to the rubbery phase. And now it's much more compliant. In this state, we apply a mechanical deformation. We change its undeformed shape to something that's deformed and desirably deformed. So we go from shape A to B. This is a manual step. We have to apply some force for it to do this. And while we keep it in that shape, we cool it down. So we just hold it and we plunge it into an ice bath, let's say. And now, because it transitioned back to the glassy phase, the Young's modulus increases significantly, and it cannot recover to the original shape anymore. So we can unload our mechanical loading force and just let it be, and it will stay in that deformed shape at a cold temperature. And this whole process we call programming. So now, that's the programming step, right? Now we have the shape by itself without any constraint in the deformed state. And the last step is the autonomous recovery. So if we heat this back up again, it will recover back to the original shape without any human assistance. So we utilize this to autonomously deploy that solar panel you just saw. So that's the mechanism. And of course, you can point out the obvious issue with this. You can only do this once, right? Once it recovers back to the original shape, you will need to reprogram it in that stuff we highlighted in pink to achieve a second recovery. But that's the notion of how do we use this inherently locked-in pre-string to exhibit autonomous change of shape. The idea is pretty simple. I mean, we use this as an example because it's something that's immediately relatable. So it's a solar panel array that's affixed to a compliant sheet and typically being pulled by a structural frame. So that's how they typically construct this, right? So they have the compliant origami with a lot of solar PV cells on the origami, and then they have a structural frame that pulls the whole thing apart. That's how they typically deploy these things. Whether it's a circular version or a rectangular version, they always have these actuators that pull the cables along and pull the whole thing apart. So that's the same kind of architecture. But we take advantage of some toys that I think a lot of you have seen or played with. it's getting more and more popular now. And it's a Hoberman sphere. You can buy this from Amazon very cheaply. We take one ring of this to simplify the geometry even more. So it's, in a sense, just a bunch of scissor mechanisms. So the Hoberman sphere or this ring are 1 degree of freedom systems, aside from tolerance and such things. You can control just one joint and the whole thing will open. And we can study a bit more deeply into the architecture of this thing, which is basically a bunch of scissor mechanisms with some sort of rotational hubs. This is something you can simply, cheaply produce either with 3D printing or injection molding or any way you want. So this is a kinematic mechanism, right? So there's no equilibrium state. At any state of the opening, it will stay in that particular state. And for us to achieve autonomous opening, that's what we want to do, we need to inject some elasticity into the system. So we take the architecture and we replace some of these rotational hubs with shaping membrane polymer hubs. So we just simply replace the freely rotating joint with something that has elasticity. So now it has a preferred state, right? This preferred state is the state we make it in. And then if we try to compress it, it will return back to that state. That's basically what we do. And now we go to what's in the middle of this solar panel. We have the ring already. Now we have the middle part, which, let me play this again. It's a flash origami. Again, a single degree of freedom system. And my host yesterday works a lot on this. So in the aeroastro department, they're using this extensively for aerospace applications. We're not the first person to discover this origami pattern, but it's very simple to make, and you can exactly see how it opens. You can fold a piece of paper, and it will do this exact thing as this person is doing. What's more confusing is with paper, you can fold it. It plastically deforms along the hinges so that you know exactly where the fold lines are. But when we 3D print this, it doesn't do this, right? So we're going to 3D print a flash sheet, and we want to fold it exactly in this pattern. So we had to study the mechanics of folding, which turns out to be a lot more involved than what I thought, because there are 2 different states you can fold into. And both of these states are energy minimums or minima of this folding at different stages of folding. So we start with pretty much the same idea. And you can see in the top is what we want. That's the thing we want to achieve. And in the bottom is the thing that we, in this case, don't want. But if we look at the strain energy of these 2 shapes, the first one costs a lot more strain energy at the initial state, but resulting in lower strain energy in the final state, whereas the second one is easier to achieve at the beginning, but more difficult to achieve at the end. But because it bifurcates from the get-go, it's very hard to control exactly which one we get into. So we had to come up with an elaborate mechanical device to make sure we overcome this thing to get to this state. Yeah.
Did I say correctly that these are the only 2 possible fold patterns?
These are the 2.
A pair.
These 2 have energy local minimums at some point along the folding path.
And there's no other folding patterns that do that?
You can fold it in other patterns, but they will probably recover back to the original state. Yeah. You can fold it any way you want, in a sense. Right. Yeah. Yeah. So that's the deal. And we control, and the other constraint we have is we control all the fold lines to fold at the same time. That's the other constraint we have. So every folding line is...
Just to follow up on that
Sure.
point, what if I were to fold it backwards and try to make it home, flip it, a lot of disk things that are bistable,
Yeah.
flip it one way, but then...
You can flip it the other way.
Yeah.
Right.
But I guess in this case, the energy in the polymer chains would be so high that
It's
it would
not bistable. And the other point is it starts off being flat. So it does not want to be up or down. Yeah. So that's a good point. So there's research now actually done by Manaria, whose initial state is already curved. Then it does become bistable, right? So if your flat state is not flat anymore, you can still fold this origami pattern, but it will never go to flat state ever again. Yeah. So there's a lot of work that goes into this particular pattern. And now we have the ring and we have the origami, both 3D printed with the same material, as a matter of fact. So everything that you see that's darker, so the entirety of this and the joints of this are shape memory polymers of the temperature we intend for it to operate on. The white stuff is also a shape memory polymer, but it transitions at a much higher temperature. So we can, for our purposes, pretend it's not reacting in that way. And if we assemble this, and you can see the autonomous expansion. So this is us submerging that small shape at room temperature under approximately 45 degrees Celsius. So at 100 degrees Fahrenheit-ish. And you can see the expansion motion follows first from the rotation, and then it gets pulled apart radially into the final shape.
Does the rate of change in temperature affect the mechanical properties, or just the rate of expansion?
So there's thermal conduction that we're not accounting for, but the stuff is very thin. Right, so it's not a continuous change. So if you imagine the Young's modulus, it's pretty much increasing very shallowly until it hits the glass transition temperature, in which it drops significantly, and then it goes as well. Yeah. So we utilize this nonlinearity, this continuous change to affect this. And so again, two things to keep in mind: we fabricate it in this state. So this is the energy-free state. The state, when I first drop it in, like this one, is the most stressed state. Right, this one, which is a good point, right? Because in the functional state, if it can deploy, it will never break. Because in a sense, the compaction procedure is the most damaging part to the material. Once it compacts into that final state, it will never experience a stress higher than this state. And the other point is, and because of the distributed nature, okay, I cannot, let me see if I can do this. Okay, there's many defects. If you look closely at the deployed state, many things have broken. Not broken, as in, it was our first attempt first or second attempt of the same structure, and because I'm not the best designer in the world, there are many things that have fallen apart. But because the actuation really comes from the strain energy of the material everywhere, every part can deploy in a sense by itself. There's nothing antagonistic against the deployment of itself. So it's very robust in a sense that it does not depend on a single point of actuation to deploy this thing. So that's the first shape-changing system that utilizes shape memory polymer to change the shape. All right, now the second, we go to a little bit different. So the first one, we went from, in a sense, a flat shape to, in a sense, a bigger flat shape, right? So there's no change in curvature if we consider this as a surface. The second one, we want to affect a change in curvature. So we want the target in this particular project, or series of projects, is we want to make something that's flat, because flat things are easy to make and easy to store because you can roll it, you can fold it, and we wanted to deploy into a 3D shape, this one, for example, that the user specify. So the user, in a sense, gave me the shape as a mesh, and we want to have a shape that's flat that deploys uniquely to this 3D shape, and once it deploys, we want it to stay deployed indefinitely. So as if we can, after deployment, tell the user, okay, we built the structure in that manner, and they wouldn't know any different. It's a local energy minimum, this one. And we use bistability to achieve this, what I just said. Okay, and we're not the first one to observe this, right? So you can see on the left, we have this conventional auxetic material, which you achieve by cutting a rubber sheet into these slits, and it opens in a mesmerizing manner, but it closes after you let go. The second one, you cut it in a slightly different manner, and once you open it, it stays opened. All right, so his hand lets go, and it stays open in the bigger state. Okay, great. So we can use this because there are several things we notice that's very important. The first is it opens and it stays opened. And the second, it opens isotropically. So it doesn't matter which direction you start pulling on this thing, its end state is always the same, and its expansion is equal in the two directions. So it opens isotropically up to the second equilibrium state, not just isotropically at the instance of the linearized quantity. So it has a Poisson's ratio of -1 across the entire string. And we use these to make very interesting things. So, and combining with this, I wanted to go down to the electronics stuff that I talked about before, right? We said soft robots must have flexible electronics. So we wanted to see if it's possible to utilize this in combination with wafer fabrication so that we can make electronics in 2D, because a lot of lithography and etching technologies does not work in 3D. You have layer-based processes. And we want to see if it's possible, after we fabricate the 2D precursor, to have it deploy whatever electronics we make into the 3D. And we use this example of an iris, not iris, a cornea, the shape of a cornea. It's not exactly spherical. It has this kind of negatively curved region and a positive curved region here. Looks like I just took a cornea from a website somewhere. And the first thing we do is to calculate exactly how much expansion we need to deploy something that's a disk to this corneal shape. And the intuition goes like this, right? So if you have a disk and you want to get a hemisphere from that disk, one easy way to do this is to in plane expand the center by a factor of 4 and the circumference by a factor of 1 in area. If you achieve that expansion, the Gaussian curvature of that disk has to change to a hemisphere. This is not exactly a hemisphere, and we used, instead of my whatever I just said, we used the algorithm to calculate exactly how much that expansion needs to be. So we do this, and we fabricate using lithography and etching on Polyimide this particular shape. And that's the tricky bit. We pull this shape off of the wafer mechanically, and we deploy this on top of the 3D printed eye of a real dimension. So this is the size of a human eye, and we're able to embed approximately 2,000 unit cells onto this cornea. So this is the kind of the roadmap of the thing I'm going to talk about. We're going to go through each bit of this so that you have an intuition of how this works. The unit cell looks like this. It's a very simple architecture. There's 4 squares that's formed by us cutting these lines out. And if we kind of rotate these squares by a fixed angle, we get this shape. And this transformation is bistable, because you can imagine initially this square is in this shape. When it's rotated by half this amount, the length of the square effectively increased, right? Because it went from the orthogonal to the diagonal, so something is getting compressed. And then when it goes all the way over, the compression eases and you go into a local energy minimum again. So that's the mechanism. And of course, if you change the theta angle, the initial inclination, and the length of the inner square, you can change what this lambda is. So the lambda is the amount of opening you get from the initial unit cell. So the initial unit cell is size capital L, the opened unit cell is size lambda times L. Right. And this lambda thing is the most important bit, because we're going to change the lambda everywhere on the surface. It's not going to be the same. Because if the lambda is the same, you just get a bigger sheet. Right? So if we change the lambda everywhere, we'll get a 3D shape. The fabrication is, if you're familiar with clean room technology, very standard. It's actually, we try to make it as standard as humanly possible so that we don't depend on any specialized techniques to do this. So we spin coat 2 layers of polyimide, and then we spin coat a photoresist on top, and then we use a digital masking system to pattern the geometry, and then we etch down the grooves. And this is actually the only specialized step number 4, is that we peel it off. Once we peel it off, we do a secondary etching, and then we get the final specimen. So that, in a sense, you could replicate this if you're familiar with clean room technology in like a day or 2. It's really simple. And we characterize the mechanics of these unit cells. So like I said, we can arbitrarily change both the inclination angle and the inner square length. And if we change those 2 quantities, we can change where the second equilibrium resides. So how big it opens before it stops. and that's quite useful, right? We know exactly how much it's going to open. So if we were to pull on the sheet, we can measure the force it costs us to pull on the sheet. And you can see initially the force increases, so it gets harder and harder to pull. And at some point, because it snaps, it goes, the force of continual pulling is actually holding it back from going bigger, because it's like a light switch, right? Once you go over the half point, you kind of have to hold it down, otherwise it'll just snap. So there's a negative force as you trying to keep the light switch in that uncomfortable position as it goes. The same thing happens here. So with different unit cells, you get different second equilibrium, so how big it goes before the force hits zero again, so you add an equilibrium. And you can also control what the tension stiffness is at the second equilibrium. Because keep in mind, once we deploy the structure into 3D, it will stay in that 3D shape. And all we care about is the Young's modulus of the material in that deployed state. We don't, in a sense, care about the Young's modulus of the material in the flat state. It's kind of irrelevant at that point. Yeah. Sure.
I feel like this graph is like pretty helpful for asking a question.
Sure.
Is that if the point where it enters the you have like different lambdas across the sheet, right? So like
You used to have different lambdas.
Sorry. You can have different lambdas or different like L's across the sheet.
Yes.
So you can imagine having like different parameters such that like some areas of the sheet requires much less force to like expand.
Yeah.
Some others need more.
That's very true. Yeah.
But if it doesn't overlap at all, then like you can't expand the entire sheet by just pulling harmonics.
Right. Okay, that's a very good point. So you can see this is elastic material, right? So after you get to that second equilibrium, nothing stops you from pulling more. You could keep on pulling. It would just be here. So when you let go, it will go back to the second equilibrium. So in a sense, you could just pull the sheet much bigger than it necessarily needs to be and let go. And then each unit cell will go back to their respective second equilibrium. Yeah, so that's what we're going to do. Yeah, okay. And then we do this very laborious experiment because we couldn't find a testing machine at this scale. It's almost too big for SEM nano indentation, and it's too small for typical testing of using instrument machines. So we had to build our own little load cell and a little specimen to use a micro stage to control this experiment. And it's a bit of a pain in the butt, but we have this unit cell that's 8x8 tessellation to see if it's indeed true that once it hits the second equilibrium, the force explodes, which it does, right? So once it reaches the second equilibrium, further pulling of the same material costs a lot of energy. Okay, great. So we have this, right? We have this isotropic expansion, and we confirmed that the Poisson's ratio is -1 across the whole thing. But all that just gets us a flat sheet that's bigger, which is not very interesting. So how do we get 3D out of 2D? So we recognize two things. One, it's bistable. And two, we can control what lambda is. And three, it's isotropic. So we can use conformal map, which is something computer graphics people do regularly to try to figure out shape change and many other different fields, to flatten a arbitrary 3D surface into a 2D plane. So the one we described with the hemisphere is how we map the globe onto a map, right? So this is how we do it, and you can notice areas such as Greenland and north of Canada is much bigger in area it's much smaller than it appears to be on the 2D map. So there's the areal distortion when we project a map onto a 2D sheet. And the argument is, if you reverse this, then you get back the hemisphere. And we do this, right? This is exactly what we do. So for a hemisphere, the equation is very simple. You literally get, with a unit circle, you can plug in 0 and 0 in the coordinate in the center to this equation, and your areal change is 4. And I can calculate everywhere along this disk what the areal change is. And once we map it, you can see, even visually you can see, right? So this square has gotten bigger by an area of 4. This yellow square pretty much stayed the same size. So this is called stereographic projection. People figured this out many hundreds of years ago, probably. But the problem is, now what if we get arbitrary mesh? right? We don't just want to do spheres. So in that way, we have to optimize by trying to minimize angular distortion as much as possible. It's not perfect, but we can do this with a mesh, and there's algorithms to minimize angular distortion while keeping, keeping isotropy as conserved as possible. And we do this. So this is part of a dome. We do this procedure. We flatten. We lay out a grid on top of this flattened 2D mesh, and from this lambda quantity at every color, we assign a unit cell that matches that lambda, and we tile them together into a heterogeneously patterned sheet. And then we make it. So you can see at the center, the unit cells look very different than at the edges. Pretty understandable, right? And now we can do this. So how do we deploy this particular geometry? It's, as you said, we take an indenter and we just keep on pushing. And we push it way past its second equilibrium, and then we let go of the indenter, and it returns to that prescribed shape. So that's the 4-stage process. We start from flat, we push, and we push past its second equilibrium. So each unit cell has extended beyond the lambda that we assign, and then we let go of the indenter, so it goes back to that shape that we decided. And simple FEM analysis confirms this exact progression. And what's more important, with the FEM, we can confirm once the indenter has left, this shape is indeed at a strain energy minimum, which shows once we deploy the structure, it will stay deployed. I mean, physically, it does stay deployed anyway, but even in absence of plasticity, so we didn't model plasticity in this particular system, it still stays in that deployed shape. And we can, of course, because it's a stable shape, we can push on it, right? So we can mechanically load that surface as if it was built in that domed shape, and it does. So we can indent it, and then when we let go, it pretty much recovers to its original state. There's hysteresis here. So there's quite a number of ways energy is dissipated as you push on this shell, but otherwise it recovers pretty much to the original state. And we can do many shapes, right? So the hemisphere was just a pedagogical example. We can do a number of very different shapes. We can do, that was the cornea. These are the two bumps with a negatively curved region in the middle. This one has a different Euler characteristic, having a hole in the middle. And then we have different shapes. So all of these have different numbers of unit cells, different ways to kind of pop them into the 3D state, and etc. And the last thing I want to show, we wanted to demonstrate is if it's possible to make a reflector out of this. So, and that's something, because I'm not an optics person, I don't exactly know how this works. As far as I know, if we have a parabolic surface, we can converge collimated light rays into a single point. That's all I know about optics. So what I did was I took a 3mm laser and I made this 3 millimeters so I can hit it with exactly the same amount of yellow visible laser. And that's the actual experiment. And the laser rays will reflect, it will converge at a focal point, and it will diverge and hit the imaging plane. And we want to see if the pattern of the image plane on the imaging plane matches what we expect. So if it does, then we can say the shape that we deployed the flat structure into is correct. And these are the four, we tried 3 different focal lengths, and you can see they're differently curved. They're all parabolic surfaces, just of different curvature. And they pretty much do what we expect them to do, right? So this is, from geometrical optics, we can predict exactly what the pattern should be of the actual deployed structure. And so depending on the focal length, you can see some patterns diverge a lot less than some other patterns. So this one diverged way beyond the imaging plane, so we can collect all the reflected lights. And we can see from the experimental photographs, they pretty much, they reflect what we predicted them to be. So that's on the microscopic scale. That's very small. And we want to do something on the bigger scale. So we actually did this before the microscopic scale, but I'm showing it in reverse. The idea is we can do them using a laser cutter and simple natural rubber. We can achieve the same behavior exactly the same behavior actually, because the generative theory behind it has nothing to do with mechanics. It's only geometrical in nature, right? So it doesn't matter. And this science popularizer on YouTube featured a video of this particular work. And so we sent him in a ladder, the flat structure, and he deployed this in England. And this video got like 9 million views because they like the shape. And so this is quite interesting, right? Because this is exactly what we wanted to do. We wanted to ship a flat thing for someone else to deploy into the 3D shape. And that's what he did. He explained this way better than I did on the video. Way better. But there you go. So that's on the like desktop scale. The last thing that we're going to do in the future with NASA, that's a render, is on a much larger scale. If we are able to achieve the same kind of bistability to deploy structure with very simple inflation-based mechanisms. As in, we stick a bladder in, we inflate the bladder, it will deploy the structure. We can take away the bladder, it will stay deployed. Okay, good. So that's mechanical bistability. On the unit cell level and on the structural level, we can use this principle to control the shape of structures, of surfaces. And the last one, I want to talk briefly about this locomotion business. So the idea is, how do we combine the two, right? So the bistability is characterized by the snapping behavior, right? Because you push it halfway and it pops to the other side. If we can use that momentum to propel something forward, that's what we want to see if it's possible. So we connect, we connect a shape memory polymer, let's say battery, I don't want to call it a battery, anyway, a power source that's a mechanical power source that's a shape memory polymer with a bistable mechanism. The idea is when this thing extends autonomously, it will push this bistable mechanism to the other state. That's the schematic, and that's the mechanism. So you can see when we submerge this under temperature that's hotter than the glass transition temperature of this material, it relaxes into its original state, which pushes the bistable mechanisms into the other state. That was the idea, right? So this is the simplest mechanism we can think of. But again, the critique here, it can do it this once, right? Once it pushes, it cannot reverse itself into the original state. So just with one stroke, it's a one-stroke robot, we can go from this state here and here. So we just connect some oars to this bistable mechanism through a pivot. It will swim backward when the bistable mechanism pushes forward. And it's able to swim a little bit. And this is pretty old work. So there's many papers that came out after this that was they basically took similar concepts and made a continuously moving forward robot using a table that's hot. So they were using, this is really smart. They had a hot table. So the material, when it touches the hot table, it transforms the state and then it rolls forward, and that piece of material gets cooled down by the air around it. So it goes back to the original state, and then it keeps on rolling. that was the invention right after this one. And we can tune this, right? So we can tune both, okay, this video is terrible, both the time it takes to transition using the thickness of the material. So I'm just going to fast forward this. Or, because we have a multi-material printer, we can control exactly what temperature the actuator gets triggered. So at a low temperature, so 40 degree, one of them gets triggered and the other one does not, because this white material needs a 65 degree temperature to trigger its glass transition temperature. So we can kind of time this sequentially, right? We can submerge the robot in 40 degree first, have it perform some action, and then submerge it in 60, or heat up the water and have it perform the second action. And we did this kind of cheeky example where we wanted to have this robot deliver a payload, have the robot swim forward, deliver a payload, and swim back. So we did this and because I was at Caltech at the time, of course, the logo is that flaming hand. We start with a low temperature, and we swim forward. But you can see the holder of this payload and the second actuator has not been activated because this sequence is still at a 40 degree or low temperature. And then when we heat this mechanism to high temperature, it drops the payload, and then it swims back. So our 3D printer has more than 2 different materials. It's able to manufacture many, many different materials, each with a different glass transition temperature. So if we design this thing carefully, we can program the sequence of motion by just doing this. Okay. So that's a brief overview of that locomotion business. And with that, that's the end of my talk. So thank you very much. Let's see. There we go. So I showed this, and I showed 3 projects, and it's funded, like Allison said, and I'm missing some funding sources. So Toyota is going to be one here. And I also want to encourage you guys to consider 3D printing as a journal to submit your new work to, because a lot of this work, so this one and kind of this one, but also definitely this one, we all use 3D printer to make this prototypes that function and demonstrate our concepts. So it'll be really interesting to hear what you guys do. Thank you very much.
I actually have one question.
Yeah.
In the first project,
Sure.
we were showed how tandem can potentially default into 2 shapes, have a energy curve with respect to the amount of differential, right? And the 2 curves have very different initial profile. Does that mean the one with a smoother profile is much easier to get into? So we don't have to worry too much about getting into the other mode because it's very difficult to provide the correct quality.
That was the problem. This one.
Yeah.
Wait, next one. Yeah, so at first, again, we fabricate this in a flat state, and we had to come up with a way to make it compact. We had to fold it somehow. But keep in mind, to fold it, we need to submerge it in hot temperature, which means it wants to unfold immediately, right? Because it wants to relax. So we have to keep everything held as we fold it into that shape. So when we tried to do this first, it kept on doing this, and we didn't know why. It kept on doing the second row of sequence of motion. So we tried to fold it, and all of a sudden it would just pop up. It would just keep doing this. And that's not what we want, right? We want a compact state that looks like this. That's what we wanted. So we had to come up with something that's, we thought it was innovative, but people figured this out many years ago. So what they would do is putting a center pillar and connect all the points in the center to this pillar and start turning this pillar. And that naturally winds this whole thing into a disk. And people have invented this in the 60s with a very large shape. Yeah. Yeah.
Can I ask a bigger picture, maybe even philosophical question about the design of these various mechanisms? Right. The shape of the slits, or in this case, the pattern of the fold. So it seems like people discover these through a combination of creativity and maybe some kind of mathematical formulation and maybe sometimes computational optimization. What do you think are the best way to come up with these various types of designs, and is there a role for AI in that process?
Interesting. Okay. The AI bit, I'm not 100% sure because I never used AI extensively. So how we approach these problems, especially the second one, that's very indicative of what we try to do. So this would be almost impossible to design by hand. So right, given the 3D shape, there's no intuition on how to flatten it. So one way that was invented in Denmark back in the day was topology optimization. So this was, you specify typically a mechanics-based goal like minimizing strain energy, and it will synthesize a structure, right? So it will assign a grid, and it decides whether the density of each unit in the grid is 0 or 1. 0 means there's material, 1 means there's no material, or vice versa. And you can 3D print it, right? So whereas here, we borrowed some geometrical intuition that considers no mechanics at all to see if we can start from something that's already kind of working. And then we use gradient-based optimization to get it to work better. So we don't start from a blank canvas. So that's what we typically do with this one. There are several other works just focus on deployable structure, like with inflatable structures and everything. That was our approach. With AI, okay, let me think. I don't know how to obtain enough training data to solve this very ill-defined problem, right? I don't even know how to define the problem in a sense. So for optimization, this is quite tricky, right? Because we want to optimize the flat state, but let's say the error minimization happens in the 3D state. So for every iteration, you will need to simulate the deployment and then measure how close that deployed state is to the idealized version, and then use that error and differentiate it by the shape of the flat state. And then do this many, many, many times until you get something that you want. So that would be the approach. And I don't know how to involve AI in this. That's my question. I don't know.
How accurate do you think simulations are of these kinds of materials or metamaterials?
Pretty accurate. So it's more the computational cost, that's the problem. So it's quite a well-defined problem. We apply the force and it goes through the second state and it goes into the... So that's fine. But this particular simulation may cost 30 minutes of a lot of computation time. So if we want to iterate, so the deploy state may be accurate to your current geometry, but it may be very wildly off from the geometry you want. And then there's no clear path to iterate because it will take many months to simulate this 1,000 times to modify each individual. There are many geometric features in this flat state. Yeah, that would be the tricky bit. Yeah. Yeah.
It's sort of a prominent question. Is there like a vocabulary or grammar of popular tessellations of patterns that you know that tend to have geometric features that do stuff that you want? Or do you have to come up with all these from scratch?
Yes, actually. Let's look. Oh, there's not a book on this. That's answer number one. But there are algorithms to generate such vocabulary. For targets, that's simpler than this. So if we want, for example, okay, there are two things. One, we know the bounds of what's feasible. So for example, if you take a square unit cell, the two ends are, one is empty square, so no material, one is filled with material. So those are the bounds. And we are very good at this moment to get any linear elastic behavior we want. So any Young's modulus between 0 and that extreme end, we can probably target. It's not unique by any means, but we can get one, at least one. And we can also target an isotropy or isotropy. Any isotropy we want, we can get it in 2D and in 3D. But those are linearized properties, right? So the problem becomes very ill-defined when instead of just saying, I want the linearized property, but I want the entire stress strain curve. That becomes a very tricky problem. We're starting to solve this now, but it's very ill-defined because we can sample all string space, like we can pull this block of material in every direction to any amount, and we have no idea what resolution we need to get the structure we want, or to get a behavior we want. There's no intuition. Yeah, we're starting to do a little bit of this. So one very contrived problem we had was how do we make a material linear elastic as much as possible? So like you have a spring, right, that exhibits linear elastic property, but of course if you straighten it into a rod, it's not going to be the same as a spring. But we want to see if we can extend the spring behavior as much as possible. And that's doable, it's just very difficult. But of course, if we change the stress strain curve to something that's like this, it'll be completely different. Yeah. Hey. Yeah.
Realistically, how many times can you morph between the shapes?
On the big scale like this one, on a small scale it's very difficult to do because we don't have enough dexterity to manipulate those tiny things. But this we done like over a period of 3 years, probably 1,000 times. So we just keep on playing with it, like it's a desk toy, right? Just keep on I'm very fidgety, so like it's a fidget spinner for me to just keep on doing this.
You have samples for us to
Yeah,
take.
I'll send you some. I was putting those in mail.
You gave me one already, but my daughter stole it like years ago.
I will make more and I'll send it to you. It's very cheap, so this is a nice way to